Alright, so this is going to be section 1.5. And section 1.5 connects really nicely to the last section. In section 1.4, we studied instantaneous rate of change. And we're going to continue studying instantaneous rate of change, but we're going to be a little more globally generic in this section. In the last section, we found the instantaneous rate of change at a specific point for a function. So like we could have done something like this. If I gave you a function f of x equals x squared plus 3x minus 4, I said find the instantaneous rate of change at, let's say, x equal to 2. And what we would have done is we would have made 2 points. We'd have went to point 2 comma something and 2 plus h comma something. So just to review, I'll do this. When I find the 2 comma something, I'd plug 2 in for these x's. So I'd go 2 squared plus 3 times 2 minus 4. Then I'm going to go 4 plus 6 minus 4. That's 10 minus 4, which is 6. So there's my x1, y1. And then for my x2, y2, I'd go 2 plus h squared plus 3 times 2 plus h minus 4. This is going to be 2 plus h times 2 plus h plus 3 times 2 plus h minus 4. FOIL this. First are 2 times 2, which is 4. Outers are 2 times h, which is 2h. Inners are h times 2, which is 2h. Last are h times h, which is h squared. Then work on this parentheses. 3 times 2 is plus 6. 3 times h is plus 3h. And then I have the minus 4. Combine like terms. Let me see that the h squared is going to go first. And then for the h's, I have a plus 2h, a plus 2h, and a plus 3h. That will give me a 7h. And for the numbers, I have a 4, a plus 6, and a minus 4. That's going to give me a plus 6. So this is going to be h squared plus 7h plus 6. And now the instantaneous rate of change, instantaneous rate of change is the limit as h goes to 0. In the numerator, y2 minus y1, so h squared plus 7h plus 6, which is y2, minus y1, over x2, which is 2 plus h, minus x1, which is 2. In the numerator, the 6's cancel, and the denominator, the 2's cancel. So I get the limit as h goes to 0 of h squared plus 7h in the numerator. And in the denominator, I just get an h. I'm going to factor out an h from the numerator, so it's going to be the limit as h goes to 0 of h times h plus 7 over h. The h's cancel, leaves me with the limit as h goes to 0 of h plus 7. That's just going to be 0 plus 7, which is 7. So the answer to the instantaneous rate of change at x equal to 2 is 7. It's instantaneous rate of change. And of course, I could have got that number on my calculator. I could have just taken the function and graphed it. So turn my calculator on, graphed y equals clear x squared plus 3x minus 4. And just go to a zoom standard for this. I think this is a small enough function that a zoom standard will work just fine. Gives me a parabola, and then I would second calc dy dx, type in the number 2, and I get 7, just like I knew I was going to get. Now, that's kind of what we did last section, and we also did some graphing. I should probably talk about this graph and how the instantaneous rate of change shows up on that graph, just to refresh your memory. So on a graph, the instantaneous rate of change is a line that essentially connects 2 points that are microscopically close. That line that we draw is called a tangent line. So if I was to graph this instantaneous rate of change, I'd copy a graph of this parabola. Let me find the vertex. So I'm going to do second, calc, minimum, trace here, trace back here, and trace here. So the vertex is at negative 1.5, negative 6.25. So when I go to graph this, there's negative 1.5, and down here is maybe negative 6.25. So my vertex is at the point negative 1.5, negative 6.25. I get this nice parabola. And it goes through the important point, 2 comma something. Let me find out the 2 points. I'll do second, calc, value, type in 2. Goes through the point 26. I'll just call this the point 126. So that's a picture of the graph, and the instantaneous rate of change is this line that goes through kind of 2 points that through the point 26, and then a dot that's basically right on top of the point 26. This right here is called the tangent line in this section, and its slope is what the instantaneous rate of change is. So the line that we've been drawing, we're now going to start calling this a tangent line, and the instantaneous rate of change is the slope of that tangent line. So that's everything that we did, and then starting to introduce some new terms. So there's nothing here that we didn't do in the last section or two. We found instantaneous rates of changes for functions by finding x1, y1, x2, y2, and then took the limit as h goes to 0. We even graphed it, and we showed the line and the slope of the line being the instantaneous rate of change. In this section, that line that we've been drawing, we're going to call the tangent line. What would happen for this function if now I change this? I want to find the instantaneous rate of change, but I want to find it at x equals 3 as opposed to x equal to 2. Well, then what I would have to do is I'd have to create 2 points, 3 comma something, 3 plus h comma something, and go through the whole procedure again. That's a lot of work. And if you're going to have to do more than one instantaneous rate of change for a particular function, it would be nice to have a generic equation that you could use. And that's what we're going to do in this section. The formula we're going to create a formula that will allow you to compute the instantaneous rate of change for a specific function for any value of x, not just a specific value. So that formula is going to tell me that the instantaneous rate of change for this function at 2 is 7. Let me do let me show you how to do that. And it's not particularly, well, it's not hard to do, but it's messy to do. So we have this function, and I found out that the instantaneous rate of change at x equals 2 is 7. What I'm going to do is I'm going to create a formula that I could just plug 2 in for x to get that value of 7 out. And the formula that allows you to compute an instantaneous rate of change for any value of x, that's called a derivative. So a derivative is a formula that allows one to compute the instantaneous rate of change for any value of x. It's not terribly hard. It's just more, it's a little bit harder because it's more, well, it's more powerful. So I need to create 2 points. I need an x1, y1, and an x2, y2, and I'm going to do the limit as h goes to 0 to get my instantaneous rate of change. The first point, its x value is just going to be any arbitrary x. And just like when we're doing with numbers, the second point, its x value is going to be x plus h. So this is just exactly what I did for the instantaneous rate of change at x equal to 2, except now, instead of using a specific number like 2, I'm using a generic x, which makes me use a generic x plus h. It's going to make the y's be messy too, but the power for this is that it's going to make it so I can find the instantaneous rate of change for any value of x. For this x right here, the y is just that, because f of x is x squared plus 3x minus 4. For this x plus h, that's crud. In order to find out what the y is, just like I found the y when I was using 2 plus h by plugging 2 plus h into those x's, I'm going to have to plug x plus h into these x's. So to get what this y is, I'm going to have to go to that x and make it an x plus h, to that x, make it an x plus h, and then a minus 4. In this section, we're going to do x plus h squared a ton of times. I'm going to do it once on a separate sheet of paper so that every time I have to do x plus h squared, I just know what it is, and I'm not going to do this computation 800 times because it's just silly. So x plus h squared is x plus h times x plus h. First are x times x, which is x squared. Outers are x times h. That's just plus xh. And I'm going to put a 1 in front of that because it's probably going to help here in a second. Inners are h times x. That's another plus xh. I'm going to put a 1 in front of that because there is an implied 1 in front of that. And the last are h times h, which is plus h squared. So if I combine the inners and outers, I get x squared plus 2xh plus h squared. In this section, I'm going to be doing x plus h squared a bunch. Every time I see x plus h squared, I'm just going to change it to that. So to get this y value, this x plus h squared is x squared plus 2xh plus h squared. And then I have a 3 times x, which is plus 3x. And then a 3 times h, which is plus 3h. And then a minus 4. I don't think one single thing combines or cancels here. So my y coordinate for y2, it's going to be x squared plus 2xh plus h squared plus 3x plus 3h minus 4. So those are my 2 points. And I'm going to do exactly what we did. To find an instantaneous rate of change, I find the limit as h goes to 0 of y2 minus y1 over x2 minus x1. So let me keep going with this. So the instantaneous rate of change, which is called the derivative now, the derivative equals the limit as h goes to 0 of y2, which is x squared plus 2xh plus h squared plus 3x plus 3h minus 4. That's y2 minus y1. And now because y1 isn't just a single number, I have to put it in a parentheses. y1 is x squared plus 3x plus 4. Minus 4, should I say. And then all over x2, which is x plus h, minus x1, which is x. It turns out that the denominator always comes out to just h, should I say, and sometimes we just don't even do it. We just write an h in the denominator, because every single instantaneous rate of change problem, the denominator just comes out to h. Keep going with this. So now I'm going to get equals the limit as h goes to 0 of, I'm going to clear the parentheses in the numerator by changing some signs. So I'm going to get a minus x squared, change the plus 3x to a minus 3x, and then change the minus 4 to a plus 4, and then the denominator is going to come out to be an h. And now I'm going to combine like terms, and lots of things are going to cancel. This x squared and that minus x squared cancel. This positive 3x and that negative 3x cancel. This negative 4 and that positive 4 cancel. So now I'm left with the derivative is the limit as h goes to 0 of 2xh plus h squared plus 3h over h. If I plug in 0, I'm going to get a 0 in the denominator, which is undefined. So I'm going to need to factor and cancel. I'm going to factor and cancel by pulling an h of a common factor out of the numerator. So I'm going to get h times 2x plus h plus 3 over h. Cancel out my h's, and I get the limit as h goes to 0 of 2x plus h plus 3. Now I'm going to plug in 0 for h and get 2x plus 0 plus 3, and that's 2x plus 3. So the derivative of this function, which is a formula that allows me to calculate the instantaneous rate of change, is 2x plus 3. We need to give a symbol for the derivative. If the original function f of x was called x squared plus 3x minus 4, the symbol that we give to represent the derivative, we just take this function notation and we put a little prime, a little kind of prime there. And this tells me that this is the formula that will allow me to find the instantaneous rate of change for any value of x. So when I did part 1, or the beginning of this, and I found the instantaneous rate of change at x equal to 2, I did all this work. If I had this function handy, if I put 2 in for the x, if I did f prime of 2, I'd go 2 times 2 plus 3. That's going to be 4 plus 3. That's going to be 7. The power of this now is for any value of x that you give me, I can find the instantaneous rate of change. So my calculator can find it too. So what we did before is I did something like this. I graphed that function, and I did like second calc dy dx. I typed in 2, told me the instantaneous rate of change at 2 is 7. If I wanted to find the instantaneous rate of change at 3, I would just go second calc dy dx 3, and I'd get 9. Well, the beautiful thing about having that formula, if I plug 3 into this formula and did f prime of 3, it's going to give me 2 times 3 plus 3, which is 6 plus 3, which is 9. So the derivative is a formula that will allow you to find the instantaneous rate of change for any value of x. And you get it exactly the same way that we did instantaneous rates of change in the last section. Specifically, I create 2 points. The first point's x value is going to be x. its y value is going to be the function value. The second point, its x value is going to be x plus h, and its y value is going to be a mess. It's going to be what I do, what I get out when I plug in x plus h's for each of the x's in the original function. And then I do exactly the same thing. I find the limit as h goes to 0 of y2 minus y1 over x2 minus x1. In these kinds of problems, because the y1 is more than one term, it needs to go in a parentheses, and then I just do exactly the same math. So in some sense, there isn't anything new in this section. It's just more generic and more powerful. So now I'm finally going to get into the section, and we're 20 minutes into the video, so this is going to be a long video to say the least. The first 4 problems, I don't know how well my graphs show up here, but they introduce that word tangent line. And a tangent line is a line that gives you, well, the slope of a tangent line is the instantaneous rate of change at a point. So when I go to do problem 2 gives me a graph, and on that graph, a line is drawn, and it goes through this point, -2, 4, and what it is, it's the tangent line. It's the line that measures the instantaneous rate of change. It goes through the point 2, -4, and a point microscopically close to the point 2, -4. So this line represents the instantaneous rate of change at this function at the point -2, 4. And the instantaneous rate of change is a slope of a line, and that line is called a tangent line. To find the slope of this line, I just need to know how to move from one point to another, and that means I need to find another point. And there's another point on the line. This is another point. And how do I find a slope? Well, I measure the y distance that I change in the x. To get from this point to this point, only going the y direction first and the x direction second, I go down 1, 2, 3, 4. So I'm going down 4 and right 1. So the slope of the tangent line of the line that measures the instantaneous rate of change, which is called a tangent line, is -4 over 1, which is -4. For your problem, the line is drawn in. To move on your line from one point to another point, you can go from the point 2, 4, you can go to that point, or you can go to this point. If on yours, to find the slope of that line, if you did this way, you'd go down 1, 2, 3, 4. That's down 4, and then back that way, left 1. It would be -4 over -1, which is +4. If you went this way, you'd have to go up 1, 2, 3, 4, and then right 1. And it would be +4 over 1, which is 4. So we're just going to start making connections between what we did in earlier sections and the more generic, powerful concepts that we're going to learn in this section. There isn't going to be anything new, but we're going to be introducing new names and new terminology. And that's the tricky part of calculus, is you get a barrage of names that mean the same thing. And that gets hard, but you'll get through it, and even if you don't completely perfectly understand it, we'll make it so you understand it well enough, and just well enough to at least get an A. And then when you take if you take the second semester of brief calculus, well, you'll understand better what you did this semester. So problems 3 and 4 give me a graph, and they have a point for the instantaneous rate of change. I don't know how well this shows up, so we need to have 2 points. So on yours, we have a line that's drawn, and it goes through the point 0, 1 and the point 4, 2. So if you wanted to find the slope of that tangent line, this line that you can barely see, those are 2 points that you can use. It also goes through, looks like it goes through the point 8, 2. So you have to figure out to describe if you're going up and over or down and left to figure out the slope of that line. And I'll do the same for problem 4. I'll find the slope of my tangent line. It goes through the point 1, 1, and it goes through the point 5, 3. To get from my starting point to a point that I know the coordinates of, I do the y direction first. It's up 2, so the numerator is going to be positive 2. Down is negative, up is positive, and right is positive, left is negative, and right 4. So the slope of this line, which is the slope of the tangent line, or it's the instantaneous rate of change at the point 1, 1, is 2 over 4, which is a half. All right. So now we're into the grunge coming up right here. In each of the problems between 5 and 14, we're asked to do two things. We're asked to find the derivative, and then we're asked to evaluate it at 4. The evaluating it at 4 part I could do on my calculator to check if I'm right. The finding the derivative, a derivative is a formula that I get by using generic points. So the first, I'm going to attack problem 6. I'm going to find the derivative, and the derivative, I need to get 2 points. My first point is going to be have the x and the function value, x squared minus 5x plus 7. My second point needs to have x plus h and something, and I don't even know if I gave myself enough room. To figure out what the y coordinate is here, I take those two x's and change them to x plus h. So it's going to be x plus h squared minus 5 times x plus h plus 7. I'm going to use that x plus h squared as x squared plus 2x plus xh plus h squared for that. So this is going to be x squared plus 2xh plus h squared minus 5x minus 5h plus 7. That's going to be the y coordinate of the second point. So the second point's y coordinate is x squared plus 2xh plus h squared minus 5x minus 5h plus 7. The derivative is a formula for instantaneous rate of change, and it's just the limit as h goes to 0 of y2, which is this long mess, x squared plus 2xh plus h squared minus 5x minus 5h plus 7 minus y1, which is x squared minus 5x plus 7. That's barely readable. That's x squared minus 5x plus 7 inside of parentheses all over x2 minus x1, which is x plus h minus x. Usually we don't even do this. We just write an h down there because I can subtract those easily enough. Now let me clean this up by getting rid of the parentheses. So I get the derivative f prime of x, which is a formula for the instantaneous rate of change, is, write all this stuff again, x squared plus 2xh plus h squared minus 5x minus 5h plus 7. Now change all these signs. The positive x squared is going to go to negative x squared. The negative 5x is going to go to positive 5x. And the positive 7 is going to go to negative 7. And the denominator is going to be just an h. Everything in the numerator that doesn't have an h should cancel. This x squared and that minus x squared cancel. This minus 5x and this plus 5x cancel. And this plus 7 and this minus 7 cancel. Everything that's left in the numerator has an h. Now I'm going to factor out that h. So I'm going to say the derivative, which is a formula for the instantaneous rate of change, is a limit as h goes to 0. Factor out an h from each one of these. From that 2xh, if I take out an h, I have a 2x left over. From that plus h squared, if I factor out an h, I have a plus h left over. And from that minus 5h, if I factor out an h, I have a 5 left over. Now I can cancel the x's, makes the fraction go away. So I get the derivative f prime of x equals the limit as h goes to 0 of 2x plus h minus 5. I probably didn't really need the parentheses anymore. And now I'm going to plug in 0 for h. I get 2x plus 0 minus 5. And that's 2x minus 5. So in terms of my work, I'm done with the grungy part of my work. If I look at the instructions, it says use the definition of the derivative to find f prime of x. So in terms of my answer, for part A, I'm going to say f prime of x equals, and it's going to be that without the 0, 2x minus 5. And then part B says find f prime of 4. All I need to do for part B is plug 4 in for x. So to do f prime of 4 is going to be 2 times 4 minus 5, which is 8 minus 5, which is 3. So for part B, f prime of 4 is going to equal to 3. I'm going to check part B on my calculator because I can. And if part B is right, then probably part A is right. So to do this on my calculator, I'm going to graph the function y equals x squared minus 5x plus 7. Graph it. And then I'm going to go second trace, go down to option 6, dy dx. I'm going to type in this number 4, and it better give me 3 for an answer. And it did. So I'm pretty sure my part A is right because my calculator can do part B, and it came out okay. Alright, so you should try to make the same effort at doing problem 5 that I did for problem 6, which means you have to find your 2 points and then do the formula for instantaneous rate of change, y2 minus y1 over x2 minus x1, take the limit as h goes to 0. Alright, so 7, 8, 9, and 10 are exactly the same things. So for part 8a, I need to get 2 points. The first point is going to be x comma 3x squared minus 4. And then the second point is going to be x plus h comma. And then to figure out what that is, I have to go 3 times x plus h squared minus 4. X plus h squared is x squared plus 2xh plus h squared. So this is going to be 3 times x squared plus 2xh plus h squared minus 4. That's going to be 3x squared plus 6xh plus 3h squared minus 4. That's my y2. So my y2 is going to be 3x squared plus 6xh plus 3h squared minus 4. Now I'll find the derivative. The derivative f prime of x equals the limit as h goes to 0 of y2, 3x squared plus 6xh plus 3h squared minus 4 minus y1 in a parentheses, 3x squared minus 4 over x2, x plus h minus x1. Again, usually we don't even do that. We just put an h in the denominator. So let me clean up that numerator. I'm going to get rid of the parentheses right in place here. When I get rid of the parentheses, you get a minus 3x squared and a plus 4. And that's going to make this 3x squared and that minus 3x squared cancel. This minus 4 and that plus 4 cancel. So I will be left with the limit as h goes to 0 of 6xh plus 3h squared all over h. I'm going to factor out an h from the numerator. I get the limit as h goes to 0 of h times 6x plus 3h all over h. Cancel the h's. I get f prime of x equals the limit as h goes to 0 of 6x plus 3h Now I'm going to plug in a 0 for the h. I get 6x plus 3 times 0, and that's just 6x. So that's the formula for the instantaneous rate of change. That's the answer to part 8a. So when I go to do this, 8a, f prime of x equals to 6x. For 8b, it wants to know what f prime of 4 is. And to know what f prime of 4 is, I just plug a 4 in for that x. It's just going to be 6 times 4, which is going to be 24. I'm going to check 8b on my calculator, because my calculator can do that. And if my 8b is right on my calculator, my guess is that my 8a is right. To check 8b on my calculator, I graph the function y equals 3x squared minus 4. Graph it. Be nice to see. Yeah, that's good. And now I'm going to do second calc dy dx. Type in the number 4. And if it comes back with a 24, that's the slope of the tangent line. That's the instantaneous rate of change. And I know my answer is right. And it came out. So it perfectly did that perfect. All right, so you should try to do number 7. It should be the same procedure. And then I'll move on to do 10. You can try number 9. All right, so 10, to do part A, I need 2 points. The first point is going to be x comma 5x squared minus 6x plus 1. The second point is going to be x plus h comma, and it's going to be a mess. To get the second point, I have to go 5 times x plus h squared minus 6 times x plus h plus 1. This x plus h squared is x squared plus 2xh plus h squared. So it's going to be 5 times x squared plus 2xh plus h squared minus 6 times x plus h plus 1. So this is going to be 5x squared plus 10xh plus 5h squared minus 6x minus 6h plus 1. Nothing combines, so y2 is going to be 5x squared plus 10xh plus 5h squared minus 6x minus 6h plus 1. The derivative, which is a formula for the instantaneous rate of change, which is the same thing as the formula for the slope of the tangent line, f prime of x equals the limit as h goes to 0 of, oh my gosh, y2, 5x squared plus 10xh plus 5h squared minus 6x minus 6h plus 1. And then I do minus y1, which is minus 5x squared minus 6x plus 1. I'm going to change, so it's minus 5x squared. It's minus parentheses 5x squared minus 6x plus 1. I'd put it in a parentheses and then I drop the parentheses. When I drop the parentheses, I'd get minus 5x squared plus 6x minus 1. And then the denominator is x2 minus x1. Now the numerator, anything that doesn't have an h should cancel. This 5x squared, that 5x squared cancel. This minus 6x, that plus 6x cancel. This plus 1, that minus 1 cancels. So I'm left with f prime of x equals the limit as h goes to 0 of 10xh plus 5h squared minus 6h all over an h. Factor out an h from my numerator. I get f prime of x equals the limit as h goes to 0 of h times 10x plus 5h minus 6 over h. Cancel out the h's. I get f prime of x equals the limit as h goes to 0 of 10x plus 5h minus 6. Plug in 0 for h. I get 10x plus 5 times 0 minus 6. That's just going to give me 10x minus 6 because the 5 times 0 is going to cancel. So the answer to 10a, f prime of x is going to equal to 10x plus 0 minus 6, which is 10x minus 6. And then 10b wants me to do f prime of 4. I'm going to go 10 times 4 minus 6, which is 40 minus 6, which is 34. I can check part B on my calculator, but I'm not going to just to save a minute. So you should be able to give a crack at doing number 9. And I will move on and do 11 and 12, which are a little bit trickier. Or I'll do 12, which is a little bit trickier. So 12 gives me a nasty point, or nasty function because of the fraction. I need to find the derivative, so I need 2 points. The first point is going to be x comma 3 over x, because that's what the y-coordinate is. The second one is going to be x plus h, and then I just need to change that x to an x plus h, so 3 over x plus h. Brief calculus gets grungy, and this is going to be grungy. So the derivative, f prime of x, equals the limit as h goes to 0 of y2, 3 over x plus h, minus y1, 3 over x, over x2, x plus h, minus x1. The denominator is easy. You just get a lonely h. The numerator's a disaster. I need to get a common denominator in the numerator. I need to take this first fraction and multiply it by x over x, and the second fraction and multiply it by x plus h over x plus h. So this is going to give me f prime of x equals the limit as h goes to 0. When I go 3 times x, I just get a 3x. Look where I'm writing that. Let me get a little carried away with that line. Let me clean that up. So I get f prime of x equals the limit as h goes to 0. This one right here is 3x in the numerator and x plus h times x in the denominator, which I'm going to write as x times x plus h. Leave this minus sign. This one I get 3x plus 3h in the numerator and x times x plus h in the denominator. And then all over h. I'm going to combine those two numerators together, and this minus sign is going to make that a minus, and it's going to make that a minus. It's going to attach to both of those. So when I attach these together, I'm going to get f prime of x equals the limit as h goes to 0 of 3x minus 3x minus 3h over x times x plus h all over h. I can't see that now. Well, in this numerator, the 3x's cancel. So this is going to give me f prime of x equals the limit as h goes to 0 of minus 3h over x times x plus h all over h. And that all over h is really messing me up. So instead of writing a fraction for that, I'm going to write a divide for that. I'm going to change this from a 3-leveled fraction to a division problem. So I'm going to get f prime of x equals the limit as h goes to 0 of negative 3h over x times x plus h divided by h. So I just made this fraction into a divide. And instead of dividing, I'm going to multiply by the reciprocal. So I'm going to get f prime of x equals the limit as h goes to 0 of negative 3h over x times x plus h times 1 over h, because dividing is the same as multiplying by the reciprocal. Now the h's are going to cancel, and I'm left with f prime of x equals the limit as h goes to 0 of negative 3 over x times x plus h Now I'm going to plug in 0 for that x. I'm going to get negative 3 over x times x plus 0, which is negative 3 over x times x, which is negative 3 over x squared. That's the answer to part A. That's a disastrous, horrible mess. It just kind of is what it is. So part 12A, f prime of x equals negative 3 over x squared. 12B, what does f prime of 4 equals? Well, it equals negative 3 over 4 squared, which is negative 3 over 16. I want to know what that is as a decimal, because I'm going to do something on my calculator real quickly to make sure I'm right. So I'm going to go negative 3 divided by 16. And this is negative 0.1875. I'm going to do 3b on my calculator. And to do 3b on my calculator, I have to graph the function 3 divided by x. Graph it. Don't care what the graph looks like so much. Now I'm going second calc, going down to option 6, typing in the number 4, and better, hopefully I get that decimal. And I'd love that. I get exactly that decimal, so my work is perfect. I'm at the point now where my video is going to pause out again. I can't really do longer than 48 minutes, which means I'm not going to get problem 14 done, but problem 11 and problem 13 work exactly the same way as problem 12. So you might have to rewind and watch me do problem 12 over as you do problem 11 and as you do problem 13, but they're exactly the same two problems. So you start off by creating 2 points. The first points are freebies, x and the value of the function. The second point, x plus h, and then just an x plus h in the denominator. So when yours is just going to be x comma 2 over x, x plus h comma 2 over x plus h. Your work's going to be exactly the same as mine. The only difference between your work and my work in problem 11 is every place I had a number 3 or a 3x or a 3h, you're going to have 2's. So if you went through my work and just changed every single 3 to a 2, that's exactly what the work for number 11 is going to be. And the work for number 13, if you change the number, my 3 to a 5, you'll get exactly what you need to get. So that will be the first half of our videos, and then we'll do more grunge in the second half. It's going to be kind of the same thing, just with a little extra, a different step added to it for a second step. So the video is about to pause out, so I'm going to just stop right here, and that's the first half of 1.5. We're almost done with the chapter, just one little video left to get through.